Hello everyone and welcome to my live, and don't forget to share as much as possible. I'm very happy for the new subscribers and a very big thank you to all of you. Let's go guys! Today, we will see together different points always on encryption. We will see the mechanism of Bitcoin, that is basically a computer file which is stored in a digital wallet app on a smartphone or computer. People can send Bitcoins to your digital wallet, and you can send Bitcoins to other people. Every single transaction is recorded in a public list called the blockchain. We gonna see Bitcoin transaction, Bitcoin script, Bitcoin scripting language. We will also see how to execute a script, proof of burn, the consequences paid to script haste, scroll transaction, and efficient micropayment. Cryptocurrency is a digital currency that uses cryptography to secure transactions and control the creation of new units. Cryptocurrency is a type of digital currency, virtual currency, or alternative currency. It can be used as an investment, a store of value, and can also be used to make purchases. It has no physical form and doesn't exist in the real world. It's not printed like dollars or euros, but it is created by people using software that solves mathematical problems and records the transactions in ledgers called blockchains. Mechanics of Bitcoin. This chapter is about the mechanics of Bitcoin. Whereas the discussion in the first two chapters was relatively generalized, this chapter will focus on a specific application of Bitcoin. It will discuss how to use Bitcoin for transactions and for storing value, and then explore some of the other ways that Bitcoin could be used in the futures. Bitcoin has been around since 2009, but it only recently started gaining mainstream attention. One thing that makes Bitcoin unique is its decentralized nature. There's no one central administrator or organization in charge of it. This means that transactions are not easily censored or blocked by governments or other organizations. It also means that you don't need to give up any personal information when you want to make a purchase with Bitcoins. Let's start with transactions, Bitcoin's fundamental building block. We use a simplified model of a ledger for the moment. Instead of blocks, let's suppose individual transactions are added to the ledger one at a time. How can we build a currency based on these transactions alone? The first model you might think of, which is actually the mental model many people have of how Bitcoin works, is an account-based system. You can add some transactions that create new coins and credit them to somebody. And then later you can transfer the coins. A transaction would be something like, move 17 coins from Alice to Bob. And it would be signed by Alice. That's all the information in the ledger about the transaction. After Alice receives 25 coins in the first transaction, and then transfers 17 coins to Bob in the second, she'd have 8 Bitcoins left in her account. The downside to this way of doing things is that anyone who wants to determine whether a transaction is valid will have to keep track of these account balances. Take another look at: does Alice have the 15 coins that she's trying to transfer to me? To figure this out, you'd have to track every transaction affecting Alice back in time to determine whether her net balance when she tries to transfer 15 coins to Dave is greater than 15 coins. Of course, we can make this a bit more efficient with some data structures that track Alice's balance after each transaction. But that's going to require a lot of extra housekeeping besides the ledger itself. Each transaction output doesn't just specify a public key. It actually specifies a script. What is a script, and why do we use them? In this section, we study the Bitcoin scripting language and come to understand why a script is used instead of simply assigning a public key. The most common type of transaction in Bitcoin is to redeem a previous transaction output by signing with the correct key. In this case, we want the transaction output to specify. This can be redeemed by a signature from the owner of address X. Recall that an address is a hash of a public key. So merely specifying the address X doesn't tell us what the public key is, and it doesn't give us a way to check the signature. So instead, the transaction output must state. This can be redeemed by a public key that hashes to X, along with a signature from the owner of that public key. As we'll see, this is exactly what the most common type of script in Bitcoin specifies, figure 3.4. But what happens to this script? Who runs it? And how exactly does this sequence of instructions enforce the above statement? The secret is that the inputs also contain scripts instead of signatures. To confirm that a transaction redeems a previous transaction output correctly, we combine the new transaction's input script and the earlier transaction's output script. We simply concatenate them, and the resulting script must run successfully for the transaction to be valid. These two scripts are script pubkey and script sig, because in the simplest case, the output script just specifies a public key, or an address to which the public key hashes, and the input script specifies a signature with that public key. The combined script can be seen in the redeeming script also comes with a key. The scripting language is stack-based. This means that every instruction needs to be executed in order and everything needs to happen in a linear fashion. In particular, there are no loops in the Bitcoin scripting language, so the number of instructions in the script gives us an upper bound on how long it might take to run and how much memory it could use. The language is not Turing complete, which means that it doesn't have the ability to compute arbitrarily powerful functions, and this is by design. Miners have to run these scripts, which are submitted by arbitrary participants in the network. They should not have the power to submit a script that might have an infinite loop. Only two possible outcomes can result when a Bitcoin script is executed. It either executes successfully with no errors, in which case the transaction is valid, or, if there's any error while the script is executing, the whole transaction will be invalid and shouldn't be accepted into the blockchain. The Bitcoin scripting language is very small. There's only room for 256 instructions, because each one is represented by 1 byte. Of those 256, 15 are currently disabled, and 75 are reserved. The reserved instruction codes haven't been assigned any specific meaning yet, but might be used for instructions that are added at a later time. Many basic instructions are those you'd expect to be in any programming language. There's basic arithmetic, basic logic, egg, if, and then statements, throwing errors, not throwing errors, and returning early. Finally, there are crypto instructions, which include hash functions, instructions for signature verification, as well as a special and important instruction called checknultisig that lets you check multiple signatures with one instruction. Table 3.1 lists some of the most common instructions in the Bitcoin scripting language. The checknultisig instruction requires specifying in public keys and a parameter for a threshold. For this instruction to execute successfully, at least T signatures from out of those public keys must be present and valid. We'll show some examples of the use of multi-signatures in section 3.3, but it should be immediately clear that this is quite a powerful primitive. We can use it to express in a compact way the concept that out of unspecified entities must sign for the transaction to be valid. To execute a script in a stack-based programming language, we only need to be able to push and pop from the data stack. We won't need any other memory or variables. That's what makes the language so simple. There are two types of instructions: data instructions and opcodes. The Bitcoin script contains opcodes, which is short for operation codes. These are commands or instructions about what you want to do. When a data instruction appears in a script, that data is simply pushed onto the top of the stack. In contrast, opcodes perform some function, often taking as input data on top of the stack. Let's have a closer, which shows the state of the stack after each instruction. The first two instructions in this script are data instructions, the signature and the public key used to verify that signature, specified in the script sig component of a transaction input in the redeeming transaction. As mentioned, a data instruction is just pushed onto the stack. The rest of the script was specified in the script pubkey component of a transaction output in the reference transaction. First, we have the duplicate instruction, op_dup, so we just push a copy of the public key onto the top of the stack. The next instruction is to op#160, which tells us to pop the top stack value and compute its cryptographic hash. The result is then pushed back on top of the stack. Once this executes, the public key at the start of the list should be replaced with a different one. In a peer-to-peer network, a proof of burn is a script that can never be redeemed. Sending coins to a proof of burn script establishes that they have been destroyed, since there's no possible way for them to be spent. One use of proof of burn is to bootstrap an alternative to Bitcoin by forcing people to destroy Bitcoins to gain coins in the new system. We discussed this use in more detail. Proof of burn is quite simple to implement. The op_return opcode throws an error if it's ever reached. No matter what values you put before op_return, that instruction will eventually be executed, in which case this script will return false. Because the error is thrown, the data in the script that comes after op_return will not be processed. So this is an opportunity for users to put arbitrary data in a script, and hence into the blockchain. If, for some reason, you want to write your name, or if you want to timestamp and prove that you knew some data at a specific time, you can create a low-value Bitcoin transaction. You can destroy a very small amount of currency, but you can then write whatever you want into the blockchain, which should be retained for the life of the Bitcoin system. Pay-to-script hash. One consequence of the way Bitcoin scripts work is that the sender of coins has to specify the script exactly. Bitcoin has a clever solution to this problem, and it applies not only to multi-signature addresses, but also to any complicated condition governing when coins can be spent. Instead of telling the sender, "Send your coins to the hash of this public key," the receiver can instead tell the sender, "Send your coins to the hash of this script." Impose the condition that to redeem those coins, it is necessary to reveal the script that has the given hash and further, provide data that will make the script evaluate to true. The sender achieves this by using the pay-to-script hash, P2SA, transaction type, which has the above semantics. Specifically, the P2SA script simply hashes the top value on the stack, checks whether it matches the provided hash value, and then executes a special second step of validation. That top data value from the stack is reinterpreted as a sequence of instructions and is executed a second time as a script, with the rest of the stack as input. The result of the second execution is then written to stout. I'm not sure what the error means, or if it's due to how I've set up this script. Getting support for P2SH was quite complicated, since it wasn't part of Bitcoin's initial design specification. It was added after the fact. This is probably the most notable feature that's been added to Bitcoin after its original specification. Plus, it solves a couple of serious problems. It removes the need for a complex response from the sender, since all they have to do is send money to the hash specified by the recipient. In our example above, Alice need not worry that Bob is using multisig. She just sends to Bob's P2SA address, and it is Bob's responsibility to specify the fancy script when he wants to redeem the coins. P2SH also has a nice efficiency gain. Miners have to track the set of output scripts that haven't been redeemed yet. And with P2SH outputs, the output scripts are now much smaller, as they only specify a hash. All of the complexity is pushed to the input scripts, but this can sometimes be quite a strange way of doing things. For example, suppose that you are shopping online and you're about to order something and are ready to pay. You ask for the address to which your coins should be sent. Now suppose that the company you're ordering from is using multisig addresses. Then, since the one spending the coins has to specify this, the retailer says to you, "Oh, well, we're doing something fancy now. We're using multisig. Send the coins to some complicated script." You might say, "I don't know how to do that. That's too complicated. As a consumer, I just want to send to a simple address." Bitcoin has a clever solution to this problem, and it applies not only to multi-signature addresses, but also to any complicated condition governing when coins can be spent. Instead of telling the sender, "Send your coins to the hash of this public key," the receiver can instead tell the sender, "Send your coins to the hash of this script." Impose the condition that to redeem those coins, it is necessary to reveal the script that has the given hash, and further, provide data that will make the script evaluate to true. The sender achieves this by using the pay-to-script hash, P2SA, transaction type, which has the above semantics. Specifically, the P2SA script simply hashes the top value on the stack, checks whether it matches the provided hash value, and then executes a special second step of validation. That top data value from the stack is reinterpreted as a sequence of instructions and is executed a second time as a script, with the rest of the stack as input. The result of the second execution is then written to stout. I'm not sure what the error means, or if it's due to how I've set up this script. Getting support for P2SH was quite complicated, since it wasn't part of Bitcoin's initial design specification. It was added after the fact. This is probably the most notable feature that's been added to Bitcoin after its original specification. Plus, it solves a couple of serious problems. Learn many things about cryptocurrencies and encryption, and also about decentralized identity management, cryptocurrencies, and encryption. If you've been waiting to find out which encryption algorithm is used in Bitcoin, we're sorry to disappoint you. There is no encryption in Bitcoin, because nothing needs to be encrypted, as we'll see. Encryption is one of many options in modern cryptography. Committing schemes are just one of the many types, involve hiding information in some way, but they are distinct from encryption. A consequence of treating public keys as identities is that you can make a new identity whenever you want. You simply create a new fresh key pair. Public keys are usually used as a form of identity verification. However, scan P via the generate keys operation in our digital signature scheme. This P is the new public identity that you can use, and SK is the corresponding secret key that only you know and that lets you speak on behalf of the identity P. In practice, you may use the hash of P as your identity, since public keys are large. If you do that, then to verify that a message comes from your identity, one will have to check that 1 P indeed hashes to your identity, and 2, the message verifies under public key PAKE. Moreover, by default, your public key PAKE will basically look random, and nobody will be able to uncover your real-world identity by examining PAY. Of course, once you start making statements using this identity, these statements may leak information that allows others to connect PAKE to your real-world identity. We discuss this in more detail shortly. The idea of creating an online persona might seem like a harmless act. However, when people create a new identity, they are faced with decisions that can lead to some serious consequences. Using this identity in public places or posting about your personal life can easily expose your true identity. You can generate a fresh identity that looks random, like a face in the crowd, and is controlled only by you. Decentralized identity management. I want to do a Bitcoin recap. Bitcoin is a digital currency that is generated by people or businesses running computers all over the world. The price of Bitcoin changes from day to day, but it's usually somewhere between $2,500 and $3,500. Bitcoin has been around since 2009 and was the first digital currency to use cryptography to keep transactions secure. There are many different types of Bitcoin, but the most popular one is Bitcoin Cash. Bitcoin Cash was created in 2017 after a hard fork from the original Bitcoin blockchain. Bitcoin is a cryptocurrency and worldwide payment system. It is the first decentralized digital currency, as the system works without a central bank or single administrator. The network is peer-to-peer and transactions take place between users directly, without an intermediary. These transactions are verified by network nodes through the use of cryptography and recorded in a public distributed ledger called a blockchain. There are many different varieties of Bitcoin available on the market today, including Bitcoin Core, BTC, Bitcoin Cash, BCH, Bitcoin Gold, BTG, and Bitcoin Diamond, BCD. Different types of Bitcoin: Bitcoin Core, BTC Bitcoin Cash, BCH Bitcoin Gold, BTG Bitcoin Diamond. It's snowing, guys. The sky is dark, the snow is falling, and it's time to get cozy. I'm not sure if you've noticed, but it's snowing outside. I don't know about you, but I'm already dreaming of a winter wonderland this year. It's time to get cozy with some hot cocoa and a good book. Here are some of my favorite winter-themed books. We want to know them. 1. A Christmas Carol by Charles Dickens. 2. The Polar Express by Chris Van Allsburg. 3. The Snowman by Raymond Briggs. I come back, my people, in a few minutes, enjoying the snow outside.